Hey everyone, just wanted to provide a quick lecture about the physical environment, chapter 2 in your textbook. So for starters, we're going to talk about various key environmental or key concepts for the chapter. And those are climate is the most fundamental component of the physical environment, that winds and ocean currents result from differences in solar radiation across the Earth's surface. There are large-scale atmospheric and oceanic circulation patterns that establish global patterns of temperature and precipitation. Regional climate reflects the influence the influence of oceans and continents, mountains, and vegetation. That there are seasonal and decadal variations in climate that are associated with the Earth's changing position relative to the sun, and also these various chemical concentrations such as salinity, acidity, and oxygen. And that last key concept, 2.6, I'm going to actually not cover very deeply because I'm going to do a lecture on water later, and this has a lot to do with water. So first, the physical environment, it ultimately determines where organisms can live. And this is because it dictates where resources are available and the rate at which populations can grow because of those available resources. So you can imagine in high altitude systems where the air is very thin, it's very cold, it's a very harsh environment, and so the resources that are available there for organisms is different than those in low-lying areas in the nearby valleys. Or you could imagine that in the northern or southern, high northern or high southern latitudes, that the climate would be the physical environment would be quite different than that which are found in equatorial regions. And so you get these very different types of ecosystems that are associated with this. So this understanding of the physical environment is therefore key to understanding all ecology. And so you can think back to when we talked about ecology, what ecology was, and it's this interaction of organisms with their environment. So this is the abiotic component of their environment that we're talking about. So we want to differentiate between weather and climate. And weather is really the current conditions outside. So you think about temperature, precipitation, humidity, cloud cover, things of that nature. This is short term. So you think about from day to day. And this sort of dictates what we wear from one day to the next. Whereas climate is a long-term description of the weather. And this is based on long-term averages and variation that's measured over decades and sometimes even centuries, and includes these daily and seasonal cycles as well as yearly and decadal cycles. So you can think about climate being what dictates sort of what your wardrobe might look like during a certain time of the year. So you may put away your winter clothes and pull out your summer clothes when it starts to get warmer. Whereas the weather may dictate whether or not you wear a t-shirt or if you are going to wear a long sleeve shirt in the summer. Also, long-term climate change results from the changes in intensity and distribution of solar radiation and changes in overall energy balance. Current climate change is due to the increase in carbon dioxide and other greenhouse gases in the atmosphere that are due to human activities. These gases absorb energy and radiate it back to the surface, creating what is known as the greenhouse effect. Remember that climate determines the geographic distribution of organisms. Climate is also characterized by average conditions, but extreme conditions are also important to organisms because they can contribute to mortality. So you can think about timing of events. So the climate may dictate that May is typically pretty warm or relatively warm, starting to warm up in a lot of places. But periodically there may be hard freezes and it can kill newly developing plants, for example. And the physical environment must also be characterized by this variability over time. So climate affects abiotic processes such as the rate of rock weathering, which in turn releases nutrients. Climate also influences the rate of periodic disturbances such as fire, rock slides, and avalanches that kill organisms and disrupt communities. But this also creates opportunities for the growth of new organisms and communities. And so when we think about the good and bad of climate change, we're really thinking about that in a sort of anthropomorphic context where we think, oh, the organisms that are being killed are are native and they're good for us to have around, and it gets into more of an ethical or moral context. Whereas from an ecological standpoint, these are just changes that are occurring. The sun is the ultimate source of energy that drives all of the global climate system. Energy gains from the solar radiation must be offset by energy losses if the Earth's temperature is to remain the same. And this is where climate change is somewhat of a concern. So to take a look at the reason that climate change is an issue, and particularly why greenhouse gases are an issue and drive climate change, you can see in the left side of the screen, you will see that we have incoming solar radiation. A lot of this incoming solar radiation gets absorbed by the surface of the Earth. Some of it is absorbed by the atmosphere before it reaches the Earth. But of that is absorbed, some of it starts to re-radiate back, or I'm sorry, some of it is reflected due to what is known as albedo. Some of that doesn't reach the Earth also because it's reflected by the clouds. So the albedo of the Earth's surface reflects some of that back. And we'll talk a little bit more about albedo later, but that can change depending on the surface that the sun's rays hit. So once there is a certain amount of energy that reaches the Earth from the sun, that is emitted as infrared radiation and is a long wave radiation. So as it releases from the Earth, that long wave radiation, it contacts these greenhouse gases and it can't pass through those greenhouse gases very well. So it is then re-radiated back towards the Earth. And so there's not that normal escape that would happen from the radiation of long wave radiation from the Earth back to the atmosphere and into space. Instead, it gets sort of trapped, it's sort of like a blanket does, and re-radiates towards the Earth and warms the Earth. And you can see that through time, carbon dioxide concentrations have increased. So beginning in the around 1958, and when greenhouse gases were first when carbon dioxide was first being recorded, you can see there's a steady increase. As a matter of fact, I believe it's about 30% increase throughout those 60 years. So we need to talk about these differences in latitude that generate where solar radiation comes into play. So you think about in the mid-latitudes, the equatorial regions, you have these areas where the amount of solar radiation coming in contacts a smaller surface area on the Earth. Whereas when you move to either the north or southern latitudes, northern or southern latitudes, that same amount of radiation, the same sort of cylinder of radiation comes in and it gets spread out over a much larger area. And so there's not as much radiation that is coming into contact per square inch of the Earth's surface. And that's why there's a colder or cooler areas in the north and south poles. Additionally, solar radiation coming in has to travel through more of the Earth's atmosphere. And so some additional solar radiation gets absorbed or deflected by albedo effects, and so it increases or decreases the temperature and increases the amount of solar radiation that is deflected. So what happens when the Earth's surface gets heated up? Well, warm air, as you probably know, rises, and as warm air rises, warm air also collects more moisture, it holds more moisture. So as the warm air rises, there's cool air that starts to come in underneath. As it begins to rise, something replaces the warm air mass underneath, and then there's cool air that comes in. And once it reaches a higher altitude, a higher elevation, that warm air cools off and condenses. So it gets smaller and smaller. The particles get closer and closer together, and the water vapor that is in there condenses, and you get the formulation of clouds. So on a global scale, this means that those areas along the equator, which get the most solar radiation per square inch, create a warm trend. So there's a lot of warming of the Earth's surface here. That warm air rises, as you can see by the red arrows. And as that warm air rises, there are these clouds that are formed in the equatorial regions, so along the equator. And once that happens, the air mass has to go one way or the other. So in the northern hemisphere, the air mass goes to the north. In the southern hemisphere, the air mass goes to the south. And these are called Hadley cells. And these Hadley cells result in the because of the high amount of precipitation due to the warming, or high amount of condensation due to the warming air masses, you get a lot of rain from these clouds in the equator, and therefore you have a lot of tropical rainforests. And as you move further north or south, you see that the air mass starts to drop. Well, remember that when this air mass starts to release its water, it gets less and less and less water. So you end up at about the 30-degree latitude, where this air mass that is now sinking because it has cooled and is starting to fall, with less and less water. Now this is important because at about the 30-degree latitude, north or south, is where you typically find the Earth's deserts. So there are other circulation cells that are associated with these patterns as well. And so the next one above or below the Hadley cell, depending on if you're in the northern or southern hemisphere, are the Ferrel cells and the polar cells. And so you can see the Ferrel cell, as this warm air now is somewhat dry, starts to drop and cool off a little bit, is pulling in this area, is pulling in a relatively warm air mass, and then it starts to again lift up because it comes into contact with the polar cell. And this is this polar front that drives or pushes this air mass up into the higher atmosphere. As it goes higher and higher, it cools off, of course, and it recirculates back towards the Hadley cell. And then the polar cell, you can see, comes down this direction, comes in contact with the Ferrel cell, pushes back up, and recirculates. Now, this area from about 60 degrees north or 60 degrees south to 90 degrees is considered the polar zone. And then from 30 to 60 degrees is the temperate zone, and then 0 to 30 degrees is considered the tropics. And so you can see that these various zones are associated with these cells. So atmospheric circulation cells create surface wind patterns, and air flows from areas of high pressure to areas of low pressure. And this results in consistent patterns of air movements called prevailing winds. The winds are deflected due to the rotation of the Earth, and this is called the Coriolis effect. And we're going to try to watch a short video here about the Coriolis effect, if I can get it to play.
Picture a circle. Here's its center, here's point A, and here's point B. Point A is twice the distance from the center of the circle than point B. Oh yeah, and it spins from its center. In 2 seconds, both points do one full revolution. But to go all the way around, point A has to go this far, while point B only has to go this far. And we all know if something travels a greater distance in a shorter amount of time, it must be going faster. So point A must be moving faster than point B. Okay, now swap out this flat circle for the Earth, and the same thing is true. All points closer to the center, say like someone in Greenland, will be spinning slower when compared to points spinning further away from it, say like people in Brazil, closer to the equator. So if we look at it all flattened out, we can picture something like this. Arrows at the equator travel faster than arrows at the 45-degree line, like we just observed. Now imagine you're a cloud that formed here on the equator. You'll have the same velocity as the Earth, but then a gust of wind sweeps you to the north, where the Earth isn't spinning as fast. Due to inertia, your speed remains the same. You don't get any faster, but everything around you is literally traveling slower, so you, relative to the ground, move ahead of everything else. If you're a cloud that forms at the 45-degree line, you'll also have the same speed as everything around you. But if you drift down to the equator, you'll be moving slower than the ground underneath you, so you'll fall behind. And the same things for the southern hemisphere. Moving towards the equator always results in falling behind, while moving away results in pushing ahead. Okay, now imagine a low-pressure cell. That means all the air around it will get sucked into the center. But the air coming from the equator will be traveling faster, so it will deflect to the right, while the air coming from the poles will be moving slower, so they'll fall behind and deflect to the left. What this results in is a circular air current spinning counterclockwise. And that's exactly what hurricanes are, low-pressure cells spinning because of the Coriolis effect. Moving this example down to the southern hemisphere, things are reversed. A low-pressure cell will still suck in the surrounding air, but now the air coming from above will be moving faster, again deflecting to the right, while the air coming from below is moving slower, again falling behind by moving to the left. This results in a clockwise spin, which is why storms in the southern hemisphere spin this way. And that's about it. It's a short video, and that's kind of the point. I hope you got what you came for. And the Coriolis effect doesn't really influence toilets, they're just really too small, and the direction of the spin more depends on the placement of jets inside the toilet. But that's it, that's the Coriolis effect. If you liked this short and to the point video, give this video a like, and if you want to see more videos like it, why not subscribe? I'll be back next week with another video, so until then, thanks for watching.
Alright, so I hope you liked that short video and you understand a little bit more about the Coriolis effect. So water has a really high heat capacity, much higher than land, and therefore can absorb and store more energy without changing temperature. And you can think about that in terms of how long it takes a large body of water, such as a reservoir or a river or the lake or the ocean, to change temperature. It takes a really long time, so it's not until late in the summer when a lake may be really warm, whereas in the winter it takes a while for the lake to cool off and maybe freeze if you're in a northern latitude. So in the summer, all our air over oceans is cooler and denser, and therefore it subsides and high pressure develops over the oceans, whereas in winter, air over the continents is cooler and denser, and high pressure develops over the continents. So this is sort of what dictates, let me see if I can, what dictates these air masses and of movement of air masses, and it's variable from during the different seasons. And so earlier I said that a lot of the deserts of the world are oriented around the 30-degree latitude. And so in the southwest, you can imagine the southwestern United States, which is very dry and arid. You would expect here in Clemson, for example, the southeast to also be a desert. But you'll notice that in July there's this air mass because of a couple of things, but we'll start with these air masses. But you'll notice that this high pressure zone pushes this air into this low pressure area and into the Gulf of Mexico, which has a lot of moisture, so it picks up a lot of moisture and it dumps a lot of the moisture into the southeastern states. And so therefore the southeast is not a desert as it would sort of be expected to be. And then in January, you see that there's a bit of a difference, and because it's cooler, we don't have to worry about, in the southeast, you don't have to worry about evaporative loss. There's a difference in July and January and the wind patterns that are generated from that. Major ocean surface currents are driven by surface winds, and so patterns are similar. There's typically a vertical ocean circulation where surface waters are warmer and less saline, so they're less dense because they don't have as much materials in them, than the deeper waters. And so these two layers typically do not mix. Where warm tropical waters, the surface currents reach polar areas, the water cools, ice forms, the water becomes more saline and more dense and sinks, and you get what is known as downwelling. Downwelling water masses move back toward the equator, carrying cold polar water. Upwelling occurs where the deep ocean water rises to the surface. Upwelling occurs where prevailing winds blow parallel to the coastline, and this causes surface water to flow away from the coast and deeper, colder ocean water to rise up to replace it. Upwellings also influence these coastal climates. Additionally, upwelling and downwelling can occur and do occur in a lot of large lakes or reservoirs during the fall and winter, or during the fall and spring. And this is because of the warming and cooling of the surface waters. So you can imagine that in the fall, the surface of a lake is losing heat to the atmosphere. As it loses heat, it gets more dense and it sinks. That sinking causes the water below it to rise, and that causes the turnover of the lake, where nutrients from the bottom of the lake that have been generated throughout the summer growing season get brought to the surface. And so this is a very important limnological process that occurs in a lot of our larger lakes and reservoirs. So as a figure to show you an example where you have wind coming down coming from north to south in this example, it causes a wind process where the ocean currents or ocean surface waters are pushed out away from the land, and you get the cold waters at the bottom, so the get pulled up to along the subsurface or the ocean surface, and this causes again, just as before, these high nutrient areas, because of the high nutrients being on the bottom of the ocean, being pulled up or upwelled along these coastal areas. And I'm going to skip that one. This is a picture or an image of these what is called the Great Ocean Conveyor Belt, and you can see again that most of the heat generated along the equatorial regions gets taken in, for example, the Gulf Stream gets taken north along this path. As it goes further and further north, it cools and cools and cools, and as it gets into these Arctic areas, it's cold enough that it starts to sink, and as it sinks, it goes actually underneath in these deeper waters underneath the jet stream, or I'm sorry, the Gulf Stream, and continues along these cold, salty, deep currents in the southern hemisphere. And this happens, and then as it moves further up again, it starts to warm up in these equatorial regions, and eventually comes in contact in sort of the areas south of Alaska here in the Pacific Ocean, again carrying this heat again across the equatorial regions back into the Gulf Stream. So average annual temperatures become progressively cooler from the equator towards the poles. This pattern is altered by ocean currents, continental topography, and the distribution of land and water masses. Air temperatures over land vary a lot more with seasons than they do over oceans, which has pretty big impacts on the distribution of organisms. So, for example, in this image, you can see that the global average temperature in the equatorial regions is much, much warmer than it is in the polar regions. Additionally, you can see in this figure that the annual seasonal temperature variation is much less in the oceans than it is over the land. So temperature also decreases with elevation, and this is considered the lapse rate. And this is called the air pressure and density decrease with elevation. There are fewer air molecules to absorb infrared radiation. Wind speed also increases at high elevations due to less friction with the ground surface. So there's quite a lot of differences in high elevation ecosystems as compared to nearby lowland elevations. Precipitation patterns associated with atmospheric circulation cells are also modified by mountain ranges and the semi-permanent high and low pressure zones. Pressure cells influence the movement of moist air from oceans to continents and cloud formation. So this is just a look at annual precipitation, and you can see where lots of the dry areas are, again, around the 30-degree latitude in the north, particularly, not as much in the southern hemisphere, except when you get over into Australia, as well as southern, I guess that's true, around southern Africa and southern South America. But you'll notice that in North America, again, we have some really dry area in the desert southwest, and then you'll notice quite a lot of dry area in this area as well. This is west of the Rocky Mountains, and this is because of the Rocky Mountains, and this sort of air is not allowed to travel back over the Rocky Mountains. And we're going to talk about a rain shadow effect in a minute. And so this area gets really, really dry as well. But remember that in the desert, or the southeast of the United States, would normally be a desert because of its longitudinal location, but because of the Gulf Stream, we don't have that effect. Coastal areas have a maritime climate, with little daily and seasonal variation in temperature and high humidity. Areas in the center of the large continents have continental climates, much greater variation in daily and seasonal temperatures, especially in temperate zones. So this is a look from city data at 2 different locations in the United States. And you'll see that in this upper panel, there's quite a lot of variation annually, right? So the average goes from about 70, 72, 73 in July, and then it goes down to below 20 for the average in January. Whereas in the lower figure, you'll see the lower panel, you'll see the annual average sticks between 70 and 80. It doesn't quite reach 80 and it never goes below 70. So you may wonder, well, where are those 2 places? Well, it turns out that the upper panel is Ames, Iowa, and so right in the sort of center of the country, and then the lower panel is Honolulu, Hawaii. So mountains do influence regional climates. Temperature decreases and precipitation and wind speed increase with elevation. Vegetation types change as you move upslope. And so if we're, for example, along the coastal California, and we have the Pacific Ocean off to the west, we have the Sierra Nevada mountains off to the east. There's warm air that comes off of the ocean, relatively warm. It gets pushed upslope. As it goes uphill, it starts to cool off. And remember that as it cools off, the moisture content gets more and more concentrated until there's condensation where there are clouds. And so you get a lot of rain on the western slopes of the western mountains. As it passes over the crest of the mountains, the high altitudes, it no longer has moisture associated with it. And so this area on the eastern slopes of the Sierra Nevadas is very arid or very dry. And so you can see here there's a western facing slope, very moist, eastern facing slope, very dry. And again, here is the Sierra Nevadas, where it's very, very high mountains, dry area over here, very moist area over this side. And if you ever have the opportunity to drive from across the Sierra Nevadas, this is a pretty distinct change. Sometimes you can even go through a pass, and as you cross through the pass, you can tell from one side of the mountain almost immediately how much drier one side is than the other. Mountains can also generate local wind and precipitation patterns. East-facing slopes receive more morning sun and become warmer than surrounding slopes and lowlands. This differential heating creates localized upslope winds. Clouds may form and produce local thunderstorms that move into surrounding lowlands. And then at night, cooling is greater at higher elevations, and this is because cold, dense air flows downslope and pools in these low-lying areas. These valley bottoms are the coldest sites in the mountains areas during clear, calm nights. This cold air drainage influences vegetation distributions in these temperate zones. Vegetation can also influence climate. So I mentioned earlier albedo, and albedo is the amount of solar radiation a surface reflects. Light-colored surfaces have the highest albedo, so they reflect the most sunlight. So you can imagine on a cold winter day where there may be a snow cover and it's clear outside, that is really, really bright, whereas in a cloudless day in the summer, it doesn't appear as bright, and that's because there's a lot more of the solar radiation that is absorbed by the plant life. So a coniferous forest has a darker color and lower albedo than bare soil or dormant grasslands, and absorbs more solar energy because of that. Vegetation can cool the atmosphere through transpiration. So this is the evaporation of water from inside the plants versus via its leaves. So in evapotranspiration, this is water lost by transpiration plus evaporation from the soil. So that is all of the evaporation, both from the plants themselves as well as the soil surface. And this can cool the local area. And again, it's because that water holds a lot of heat. And so as it evaporates, it carries a lot of heat off of the Earth's surface with it. And this transfers water and energy as latent heat into the atmosphere, thereby affecting air temperature and moisture. And because of this, deforestation can increase albedo of the land surface, where less absorption of solar radiation and less heating. This is offset by less cooling by evapotranspiration. And the decreased evapotranspiration results in less moisture in the atmosphere and therefore less precipitation. And so deforestation in the tropics can lead to a warmer, drier regional climate. So as an example, visual example, you can see that in the panel on the left, you see there is a certain amount of albedo being reflected from the solar radiation. So the amount of solar radiation coming in, some of it is reflected back. And this is, again, on the left side is vegetated, and then on the right side is a deforested area. And so then there's some sensible heat loss, and then there's latent heat loss, and that's due to evapotranspiration. But in a deforested area where there is lighter soil, there's not as much dark green vegetation, the amount of albedo effect is much greater. There is more sensible heat loss, but there is less evapotranspiration or latent heat loss. Climate has varied over hundreds and thousands of years, and this has influenced the evolutionary history of organisms and the development of their associated ecosystems. So we need to take a look at the seasonal changes that are due to the Earth's axis, tilt on its axis. And you can see that in the summer solstice, the northern hemisphere is tilted towards the sun, and in the winter solstice, the northern hemisphere is tilted away from the sun. Of course, this is what causes the warmer and cooler seasons. And then in the equinox, the autumnal and spring equinoxes, you'll see that the Earth's tilted at about the same, and therefore there is about the same amount of solar radiation reaching the Earth in the northern and southern hemispheres. And the Earth's tilt is about 23.5 degrees. So the aquatic environments also experience seasonal changes in temperature. Water is most dense at 4 degrees Celsius. Ice has a lower density than water and forms on the surface. Ice has a higher albedo than open water and prevents warming of the water. Now, this is a pretty important concept. I'm going to talk more about this in a separate lecture later, so I'm not going to spend a lot of time talking about these next few slides. Oceans and lakes can stratification determines the movement of nutrients and oxygen that are important to organisms. We talked about the turnover earlier, fall turnover, and I'm not going to go over this slide. I'm not going to talk about El Nino and La Nina right now either. You can read about that in your textbook as well as these other large-scale air mass movements. And with that, I think we're gonna stop, and we'll talk more about some of these additional chemical environments later. But you can read through that and be sure that you take the quiz on this chapter, and we'll talk to you soon.